Thank you, Justin. Hopefully everybody can hear me okay. So Justin gave the title of my talk, and I'm going to jump right in and talk about, I guess these are some active projects I've been doing over the last 5 or so years, and kind of a culmination of things I've been doing over the last dozen or so years. So, okay, before I get started, I just wanted to make some acknowledgements. The contributions in this talk come from Thomas Otheim, who's a technician in our department. He's been building our land streamers sources, helps in the field quite a bit. James St. Clair was a postdoc here up until, I guess, a year and a half ago, and he was instrumental in really helping me think more about near surface processes in the form of first arrivals and surface wave integration with reflection data. And then the 4 names after that were graduate students over the past few years, or are currently. And I'm going to be highlighting some of their research. And in this talk, I've got funding sources, or data I'm presenting were funded by the U.S. Geological Survey, U.S. Department of Energy, Department of Defense, U.S. Department of Defense, and then the Norwegian Research Council, or Research Council of Norway. So in this outline, I just thought I'd give you an outline here. And the picture on the right was from this X-ray Earth mini-series that is hosting right now on Amazon Prime. I guess it's a plug for that. But it's just a fun picture of downtown Seattle while we're collecting seismic data in the foreground. What I'm going to talk about in this presentation is I'm going to start with instrumentation, essentially sources, receivers, streamers, etc. And then I'm going to kind of highlight what I call full wave field considerations. I don't do full waveform inversions, but I do consider the full wave field. And what I mean by that is I look at first arrivals to generate P-wave velocity tomograms, typically from vertical GEOPHONEs, vertically oriented sources, Rayleigh wave signals, and then reflection signals to kind of put it all together into kind of a holistic view of what's going on in the subsurface. I'm going to focus on a couple case studies here, one from Salt Lake City, where we've looked at earthquake hazards with our land streamer system. Jump over to Charleston, South Carolina, where we're doing something very similar. And then I'm going to talk about this Crystal Geyser site in central Utah, which is an analog for a failed CO2 sequestration site. And then I'm going to talk about new directions, what I'm hoping to do moving forward. So I thought I would just start with sources. And you've seen all these pictures before, but I thought I would highlight a few things here. What sources I use, what we use for active source imaging. And the upper left is a sledgehammer with Thomas swinging the hammer on a plate sideways, generating some shear energy. And it's the most effective shallow shear wave source. And in the lower right, we have Galen Cape from UTEP operating his A200 in the shear mode. And so those are the 2 shear sources that I'm going to highlight during this talk here. And then the rest of these sources are, except for the one, are all hammer sources of a variety of scales. The lower middle one, you can see swinging a hammer in the river. We actually were hitting a rock, so we actually got decent coupling with this. Scaling up a little bit more, there's the PEG 40 here, which PASSCAL has one of these, so the community has access to this PEG 40. It's an electric motor, so there's not a lot of noise associated with the source, unlike running a generator like the rest of the weight drop sources. Up in scale, you can see our little Kawasaki Mule pulling a small weight drop. This is about maybe a 30-kilo hammer accelerated with a rubber band, you can see here. We've got a hitch mounted weight drop in the center here that is accelerated with I think this is about a 50-kilo weight drop, operated with about an 8-horsepower engine. And then a bigger weight drop here through Salt Lake City. You can see the police escort that we have in the lower left. And then I thought I would include some vibes also. This is from an experiment up in the Seattle area that we collected a few years ago. All of these sources we use in urban environments. I typically focus on weight drops simply because they're cheap, they're impulsive, so we get a nice clean signal, and they provide a really nice broadband response. And so we build sources here. There's lots of commercially available sources. They're available to the community through IRIS. Again, with this PEG 40 source, or through the seismic source facility at UTEP with this A200 source, which operates in both P and S mode. On the receiver side of things, I thought I would kind of give you a suite of what you can do, especially in an urban environment. Of course, the traditional way is to operate geophones in a planted environment. You plant it in soil with a 3-inch spike. If soil is not available, you can put a base plate on that same geophone and operate it on a sidewalk or a road or something like that. We used to, back in the day, not have access to land streamers, which I'll talk about in just a second. And in this case, this is across the Portland Hills Fault in downtown Portland, Oregon. We actually drilled into a sidewalk that was slated for demolition. Since then, we've started developing these land streamers, and land streamers have been around for a couple of decades now. I think the group out of ETH in Zurich, Alan Green's group, published the first results from land streamers back in 1999. So it's nothing new, but they really have become much more popular for operating on roads and the like, simply because you don't have to plant phones. It's significantly faster to deploy, and the data quality doesn't seem to suffer at all. We have equal data quality with planted phones, like you see in the upper right, and these streamers with base plate coupled sensors. The other benefit of land streamers, as you can see from this little diagram in the upper left, is you can put multiple sensors at any configuration that you want. You can vary the geophone spacing, you can vary the frequency of the phones, or in this case, we've got 3 components. You can see a vertical component in the middle and 2 horizontal components here. So we can record 3 component data without having to orient level the sensors or the streamer. So it's a significant time savings, and the data quality don't seem to suffer, as I mentioned. You tie all these geophones together typically with something like I'm showing here, a data recorder. These are geodes, again, available through IRIS. These are 24-channel boxes. You can see my little radio trigger box here in the foreground. So when we thump the ground, we record the response. One thing I didn't mention on the previous slide, I showed this figure on both as a reminder, but you can plug in something like this. It's called a GPS sync, and it allows you to get millisecond timing from a hammer or any other source, sledgehammer, weight drop, vibe, or whatever. The nice thing about that is if you're utilizing nodes or broadband seismometers or what have you, you have the millisecond timing that you can pull, shot, or receiver gathers back out. So these are really nice boxes. Again, they're available through IRIS, through the source facility at UTEP, and we've got one here at Boise State. The other option that, of course, is gaining popularity are these nodes, and now IRIS has a couple thousand of them. This is a node deployed at our Utah site on travertine at this site where there's CO2 naturally outgassing. And you can see we planted them in spikes right in the travertine. If you get into more difficult situations, I pulled this image in the lower right off of the Smart Solo website, where they actually have placed base plates on their Smart Solo. So I know it's possible. I don't know that the PIC or PASSCAL has any base plates for the nodes, but that's something that maybe could be inquired about. So the whole range of sensors, the benefit of the 3 component nodes is 1, you get 3 components, and 2, you have no cables that go around. So if you have large offsets between geophone spacing, etc., the nodes are definitely a better bet. The difference or the benefit to something like a geode is you see your signal in real time. So if you are concerned at all about setting acquisition parameters, doing noise tests, etc., it's very difficult to do with a node, whereas opposed to the geodes or something similar are very easy because you see this displays in real time. I thought I would just kind of throw this on here. I grabbed this morning from the PASSCAL website in terms of what does the IRIS hardware look like for high resolution. And so I just grabbed this off the web page. They've got 14 24-channel geodes, so that's 300 and some odd channels total for the high resolution system. They've got some older strativisors here. Lots of geophones. You can see these 4.5 hertz phones. There's a couple hundred of them. 40 hertz phones. There's a couple thousand of them, or 8,000 of them. And then lots of other cables, including things like snow streamers and the like. I mentioned the sources earlier, but I'll emphasize that IRIS has access, or you all have access to 2 different sources through IRIS. One would be this PEG 40, which is a 40 kilo electric motor driven weight drop. And then the other one is the A200, which is out of the source facility at UTEP. This thing runs off a 10 horsepower engine and can be operated in both P and S mode. I also just thought I would mention the ground penetrating radar equipment that are now available through PASSCAL, and a range of frequencies from 250, 500, 1000 megahertz. So there's lots of options out there. And then I thought I would also mention that vibes are available through the UT Austin NERI site, where they've got 5 vibes of various sizes. I've used the thumper, which is kind of ideal for kind of environmental work, if you will. You can operate right on city streets, and it gets bigger until you get up to T-Rex and Liquidator, which are quite large. With NSF funds, you can actually use these things for relatively low costs. If it's non-NSF funds, it gets quite expensive. I have this conversation a lot, so I thought I would discuss it a little bit. When I showed that page of equipment from PASSCAL, I mentioned that there are both 4.5 hertz phones and 40 hertz phones available. I thought I would just kind of take a minute to talk about the difference between why you would want a 4.5 hertz phone versus a 40 hertz phone for something like active source imaging. So the plot on the right shows the output voltage, output in volts per meter per second versus frequency. These are log plots. These are for 2 phones that I grabbed off of the Sercel website. So this is a 4.5 hertz phone and a 40 hertz phone. Different vendors, they're pretty much the same in terms of the response. If you don't know what spurious frequency is, it's kind of the frequency at which the geophone stops responding in a nice linear fashion. So you typically don't want to go beyond the spurious frequency, which for a 40 hertz phone is upwards of about 300 or 400 hertz. For a 4.5 hertz phone is more like about 150, 180 hertz, somewhere in there. I typically try to target 3 octaves of signal when I collect both reflection and surface wave data, I guess, or first arrivals. 3 octaves, if those of you are not familiar with what an octave is, it's, low C to middle C, if you will, in music, or 10 hertz to 20 hertz, if you will, doubling of frequencies. So 3 octaves would be, let's say, 10 to 80 hertz or 20 to 160 hertz. That's typically what we look for in the body wave world. And then in surface waves, they're significantly lower frequency, simply because they're bound by the surface. We do see surface waves. I've seen surface waves as high as 800 hertz or more, but they just don't probe very deep. And so they're not terribly useful for solid earth applications. But there is some overlap in frequencies. And if you really want to focus on surface wave energy, then grab a 4.5 hertz phone and use it, because you don't really care about the body wave signal maybe so much. And so you want to emphasize, you want to push your frequencies as low as possible to get the longest wavelength so you can probe the deepest. So these 4.5 hertz phones are pretty good. When we talk about doing like first arrival tomography, I typically like to use a 10 hertz phone, because we typically don't see off of a sledgehammer signals below about 10 hertz. And so all you're doing is you're promoting more surface wave energy coming in relative to the body wave energy, but they're first arrivals, so nothing should interfere. The challenge is when you want to work with reflection data. When I'm looking in the upper few hundred meters, I would prefer a 40 hertz phone, simply because I want to do everything I can to knock down the surface wave energy and emphasize the body wave energy. Why? Because often the dynamic range is saturated by the surface waves, and you don't typically see, or often in many situations, you don't see good body wave energy that lie beneath the surface wave window. You can try FK filters and other spatial filters to remove the surface waves, but I've often found that there's just no body wave energy that lies beneath there under a lot of situations, especially in the dry Mountain West where I live. I also wanted to just highlight this, or emphasize this energy loss from absorption. This I just pulled from the Berger textbook in terms of these response curves, but as you can see, you're losing high frequencies as a function of distance. And so by the time, at 100 meters, by the time you get to 100 hertz, you've lost about an order of magnitude of signal relative to, let's say, at 10 hertz or less. And so you're fighting this loss from absorption and other processes as a function of distance away from a source. So if you really want to focus on body wave energy, I would recommend opting for higher frequency phones like a 40 hertz geophone. So I'm going to start by talking about a study that we published this past year in the SEISMIC record. We got it in the first issue. And the title of it was "A Broad Distributed Active Fault Zone That Lies Beneath Salt Lake City, Utah." And on the left, you can see the geologic map of Personius and Scott, and you can see the superficial deposits here. And then this is my interpretation from all the seismic lines. But what we've done is identified a number of faults and folds that really suggest that we have this broad distributed fault zone. And our interpretation is that there's a connection between the one segment of the Wasatch Fault called the Warm Springs Fault and another segment called the East Bench Fault, and they are connected through this relay ramp. And so that's my interpretation, and hopefully I can show you that the data support that interpretation. So sorry, it might be loud. It's loud for me, but this is a picture. I'm going to pause the sound there for a second because it's too loud for me. This is our weight drop operating with our land streamer being pulled behind it through downtown Salt Lake City. And you can see if I continue this here, that we thump the ground, we listen for about 5 seconds, we stop, we move up, and we do the same thing again. And you can see we're right in front of a hospital here. And so we're operating right in the presence of traffic. We work right along the city streets. We have either flaggers or police escort that helped us in this particular case. For this experiment, we used 2-component 4.5 hertz geophones. I'll show you why in a second. We had 72 channels out, so we had a 90-meter aperture because we were 1.25 meter spaced geophones. That's to not alias our surface waves at the frequencies that we care about. We were acquiring about 4 or 5 kilometers per day at 2.5 meters shot spacing. We would thump the ground once, move up, and we had police escort, like I said, or flaggers. And I picked this shot gather on the upper right here for a reason. This is the unfiltered version. And the filtered version, you can see the traffic noise going through above the first arrivals here. And when you apply a simple bandpass filter, you can see the traffic noise is gone. And that's simply because vehicles, especially heavy vehicles, tend to operate at frequencies below what we care about in the upper few hundred meters. So here's a 30 to 200 hertz bandpass filter, and we removed all this surface wave energy, or the traffic noise that's generated from, let's say, 5 to 15 hertz, something like that. So with a simple bandpass filter, we're able to remove a lot of the traffic noise. In this same shot gather, you can see very strong surface waves. Here's the air wave. If you're familiar with that, it's traveling at 330 meters per second. And then this is just a blow up of the streamer itself. Same image on the upper right, but I included a dispersion image now, and you can see this nice dispersion. This is phase velocity versus frequency. And so we pull out the surface waves, look in the frequency domain or the dispersion domain, and we pick the dispersion. We invert for shear wave velocity. We pick the first arrivals here. We invert for P wave velocity for the upper tens of meters. And then what's left, we pull out the reflectivity that you see here, and we pull together a reflection section. Here's another image in the upper left of the police escort going through one of the very busy cross sections in Salt Lake City. The benefit of having police is they can do anything they want. Unlike flaggers that will not stop traffic like this, police are empowered to do what they want. And this picture here shows our weight drop right in front of the temple in downtown Salt Lake City. So we're operating right through downtown. These are just a bunch of shot gathers, raw data here and filtered, emphasizing the first arrivals, the red lines. The green dotted line is the airwave, and then the surface waves down here. So on the unfiltered record, you can see them quite clearly. This is a blow up. You can see this is only going down 0.4 of a second versus 0.8 of a second here. You can pull the dispersion out of this. We throw away signals that are less than a spatial wavelength here. You can see that grayed out area here. We pick the dispersion here with these green dots. We invert for shear wave velocity. There's lots of ways to do it. There's commercial software, and we've got some homegrown code here that we've used, but a very common package is SurfSeis, which is distributed by the Kansas Geological Survey. Lower left, you can see a comparison of some borehole cone penetrometer derived shear wave velocity measurements. Those are the red lines here, and our blue dots represent shot gathers that are close by, and you can see it's a pretty good fit. And I'm going to talk about that again in a second when we talk about the effects of the asphalt on the Rayleigh wave response. But you can see the quality of the records. The one thing to emphasize here, as I mentioned, it's really hard to get body wave energy beneath the surface wave window. You can see in this particular example, as we were climbing an elevation, the water table was dropping. So our window between surface waves and the first arrival was actually quite small, and it becomes very difficult to actually pull reflectivity out. So I think in hindsight, these were 4.5 hertz phones. I probably would have collected data with higher frequency geophones to try to allow the body wave energy to get through the surface wave window. Okay, here's an example of a cross section or a profile down 500 south. If you're familiar with Salt Lake City, it's just to the south of the Salt Palace, where if you've ever been to a large conference there, that's where you would have been located. Okay, so the top right figure is the P-wave tomogram that we've derived from this, and we've highlighted the in bold the 1500 meter per second contour. Why? Because that's a proxy for the water table. 1500 meters per second is roughly the speed of sound in water, and for saturated unconsolidated sediments, we see similar velocities. So anything slower than 1500 meters per second is typically unsaturated. Anything faster than 1500 meters per second is typically saturated. And you can see the one borehole here. Here's our water table depth. It nicely matches our 1500 meter per second contour. So we feel pretty good about that. The second figure is the shear wave velocity profile obtained from Rayleigh wave inversions. And you can see what I've done is I've contoured this by NEHRP site class. If you're not familiar with that, 180 meters per second separates very loose soil. That would be the E class from D class soils, from stiffer C class soils, etc. And I wanted to emphasize one thing here. You can see this, it looks like kind of a mushroom shape here and here, these elevated velocities along this profile. On the surface, the geology is mapped as lateral spread deposits. So when we transition from lake deposits, this is Lake Bonneville deposits from the precursor to the Great Salt Lake that's there now. Once we get into these lateral spread deposits, the soils stiffen because of reworking of these deposits, and we see elevated velocities. I like to show these common offset gathers here to kind of validate this this interpretation and observation. And what we're seeing here is, so this is a common offset gather. So this is every trace at 65 meters offset between the source and the receiver. And all I've done is I filtered this particular gather between 5 and 80 hertz. So there's no processing in the data. This is raw field data, except for a bandpass filter. And you can see the primary arrival is the fundamental Rayleigh wave. And I put these apparent velocities in here of 200 meters per second here. You're just taking this travel time, distance divided by the travel time. And you see these elevated faster arrivals here at about apparent velocity of 280 meters per second. So you can see these two are at the same scale here, that where we see these faster Rayleigh wave speeds, we get faster shear wave velocities. So if you want to question whether or not this elevated shear wave velocity is valid, we can look at the raw field gathers and say, yeah, we see elevated shear wave velocities here, or Rayleigh wave speeds, which translate directly to elevated shear wave velocities, because the Rayleigh wave speeds are mostly controlled by shear wave velocities and not, they're relatively insensitive to P wave velocities. And then at the same scale down here, you see the reflection image, and you can see nice reflectivity here. And then we see these tilted reflectors, and then again, flatline reflectors or tilted the other direction. So we've interpreted a series of faults in here, hence the interpretation that we have this broad distributed fault zone that lies beneath Salt Lake City. So that's how we've kind of pulled that together. Just to emphasize a little bit more about these common offset gathers, you can plot common offset gathers at a range of pass bands just to look at your signal quality, which I find to be very useful. Here's a 2 to 6 hertz bandpass filter, and you can see indeed that we have Rayleigh wave signals down at the pass band between 2 and 6 hertz. Those are wavelengths on the scale of about 100 meters. A rule of thumb with Rayleigh wave inversions is, you know, you're able to estimate shear wave velocities to about a half or a third of a full wavelength. So that gave us the confidence that we could interpret down to 30 meters. VS30 is a standard that geotechnical engineers use for estimating site response or earthquake engineers. And so we use that as a metric that we want to try to image down at least 30 meters with our Rayleigh waves, or with our, to measure estimates shear wave velocities. As you go to higher frequencies, you start to see, you'll see there's relatively little effect in the travel time. There's a little bit of wobble here, which tells me that at great depths, for these longer wavelengths, it's relatively we see relatively uniform shear wave velocities. As you get to higher and higher frequencies, you can see this effect. This is essentially the same figures I showed on the previous slide, where we have these elevated or earlier Rayleigh wave speeds here. And then if you apply a deconvolution, a spiking deconvolution to this, you can start to see the reflection window that kind of hides beneath the surface waves or the lower frequency signals here. This is a 30 to 200 hertz passband. You can actually see the air wave in here, but this is just a single channel, keep in mind. And in this particular data set, we had 72 channels. So hopefully you will see that we can get 72 times the signal improvement. Not really, but a significant improvement to generate this sort of image from this single channel version of that. So here's our reflection window that lies between the first arrivals, that's the red line, and the surface waves that lie beneath. This is, I'm just jumping over to Las Vegas really quick. We collected this data set this past summer, and I just wanted to emphasize this common offset gather one more time. Here's our first arrival tomogram, and you see this very low velocity zone here. This happens to be or what I'm interpreting as a colluvial wedge package here, very low velocities, enormously low velocities. And you can see it on the raw field gathers. Again, this is just a common offset gather with a simple bandpass filter, no other processing involved. And you can see these significant slowdown of the first arrivals here that's consistent with this interpretation of this colluvial wedge package. Surface waves also much slower here in this particular case. So I just like to emphasize these common offset gathers are a great tool for kind of validating the observations that you think you see in your processed product. Back to Salt Lake City really quick. I just thought I would show you, this is a roughly 5 kilometer long profile that we collected in a single day. And again, we're focusing on the upper tens of meters for the P wave image, which you see here, the shear wave velocity image here derived from the Rayleigh waves, and then the reflection image here where we see lots of offset reflectors. You can see that the shear wave velocities are decreasing farther to the west or the left here. And you can see the P wave velocities are also, there's a significant step right here in the P wave velocities. This, I didn't highlight it in bold, but this particular line right here is the 1500 meter per second contour. So you can see there's a significant drop in what we would call the water table here based on that 1500 meter per second contour. So we've gone from this unconfined groundwater system to a confined groundwater system in this case. You can see a colluvial wedge developed here in the shear wave velocity, sorry, the P wave velocities. That's quite nice across the East Bench Fault, which again is a strand of the Wasatch Fault system, and lots of faults here. You can see the data quality do change quite a bit. Our data quality suffer when our velocities go down in this case. You can see the water table drops, and you can see the data quality are not nearly as good. On this next slide, it's the same image, only I've included VPVS. So just taken the P wave velocities and divided the shear wave velocities by them to end up with this VPVS image. And if those of you that like to look at VPVS or Poisson's ratio know that typical dry soils, we typically don't see VPVS ratios below about 2.5. For rock, we typically don't see VPVS ratios below about 2. And for saturated soils, we can get VPVS ratios upwards of 10 or greater. And so I kind of showed this plot here that if you like to think in Poisson's ratio, look at the red line and the red axis if you like to think in VPVS. Look at the blue, and you can see for dry soils, we typically see VPVS ratios below 2 or around 2. This is using some empirical relationships, essentially the mudline equation, if those of you that are familiar with that. But as you increase, if I focus on VPVS for a second, when we get above saturation for this particular model, our VPVS ratios tend to get above 2.5 all the way up here. So as we get to really soft soils, we can see VPVS ratios upwards of 10 in this particular case. So that VPVS ratio really can help you, and I'll show you an example of how it can help you distinguish between dry rock and saturated soils. So combining all the data from Salt Lake City, we can look at an image like this, which is the average shear wave velocity for the upper 30 meters for all of downtown Salt Lake City. Again, the Salt Palace is located about right here. The temple is right here, if you're familiar with Salt Lake City. Prior to our study, there were 36 downhole measurements that were provided for this area. You can see them in these circles here, and we've compared and contrasted those with our data, and they're pretty good. we added an additional 15,000 shear wave velocity measurements to kind of fill in this. It's about a 5 square kilometer area. And so what you see are very low velocities in the southwest portion of the slide here, and the velocities tend to increase with increasing elevation. These are the high stands from Lake Bonneville here, these kind of burgundy colors here. And this is the East Bench Fault, and this is the Warm Springs Fault, so 2 strands of the Wasatch Fault system. And so if you want to play some games like this, you can start looking at relationships between, in this particular case, VS30, or the average shear wave velocity for the upper 30 meters, and elevation. And you can see at one of the high stands, there's this nice transition from modern marine deposits to older lake quaternary deposits here. So there's this nice inflection in this relationship. If you look at a log plot over here of slope versus VS30, you can see there's this nice log trend here. Walden Allen back in 2007 put together a global relationship for both the stable continent, that would be these red boxes here, and for active tectonic zones here. You can see for Salt Lake City and the Wasatch Front, the velocities are significantly slower than these global relationships. Of course, the motivation that Walden Allen had is if you can come up with these relationships, you can measure slope from surface topography and estimate the shear wave velocity. And the point here is that the velocities are slightly different, or much lower than the global averages that they put together. And this final map here on the bottom shows shear wave velocity, or VS30, versus the Bouguer gravity. And again, for these high stands, you can see this nice transition from lake deposits here to kind of near shore deposits here. So you can kind of play these games and try to establish regional relationships with lithology, which this is all color coded by slope, topography, etc. And if you have some calibration for doing site amplification, you can take your shear wave velocities and convert that into a site amplification map, which is what I've done here. I took the shear wave velocity versus site amplification measurements from this Williams et al. Paper and simply extrapolated it for the whole region here to come up with this map. And for the 3 calibration points that overlap with our data, it's a pretty good match, you know, amplification of 8.75 versus 8. So not bad. And you can see they looked at lots of different frequencies, and you can see our data nicely match this period band, which is consistent with our seismic data. So this would be what, 5 hertz to whatever that is. So this is about the same period or frequency band that we're looking at. So you can play all these games once you get this large database. You may have asked, or you may ask, does the road influence the Rayleigh wave speeds for the underlying soils and rocks? So Gabe Gribler, for part of his dissertation, looked at this or asked this question and modeled it with real data and compared it to synthetic data. And the answer is, or he modeled it with both a 25 centimeter thick concrete layer and a 10 centimeter thick flexible asphalt layer, 2 scenarios that we've encountered. And for the asphalt case, for high shear wave velocities, so the B class would be faster than 760 meters per second, we don't see an effect at all. And no surprise, with lower frequencies, we're probing to greater depths, we have less of an influence of the road surface. At higher frequencies or at slower shear wave velocities of the underlying soils, we have a larger effect, upwards of 20%. So that's something to consider when we do these land streamer measurements on roads that are either concrete or asphalt. There does need to be a calibration. What about multi-component data? This is from that Salt Lake data set where we were able to pull out both Rayleigh wave dispersion from the vertical and the horizontal components. And Gabe showed from this 2016 paper that we can separate prograde and retrograde signals. Many of you know that the fundamental mode of Rayleigh waves typically moves in a retrograde fashion or a counterclockwise fashion with respect to the direction of motion. Many of the higher modes propagate in a prograde fashion, and with some simple polarity mutes, as we call them, you can separate those higher modes from, or those prograde higher modes from the retrograde fundamental modes. You can also do things like you can generate these active sort of spectral H/V spectra with 2-component data. So there are some benefits to that. So moving on to Charleston, this is a data set that we're still working on. I have a student that just defended his thesis this past semester or past summer that we're still working on. But we, when we collected this data set, one of the simple observations that we made was that a lot of these dispersion curves, they all look very similar, represent what we'd expect to see in a 2-layer problem, and that is a flat relatively flat response here and this sharp kind of hockey stick type view. So we modeled this, and it turns out that for the Charleston area, there are Holocene deposits that sit on top of older tertiary deposits, and that hard boundary seems to represent a fundamental site response parameter that we care about in the earthquake community, because it's going to generate a fundamental resonance that could damage buildings. So what we were able to do was, through machine learning now, or sorry, through image processing, we were able to automatically pick the asymptote of the dispersion image for both on the vertical and the horizontal axis. And from that, we can automatically, without picking any dispersion, we can generate phase velocity curves, and we can invert for the depth and the shear wave velocity for the upper and lower layer through some modeling. What we did on the machine learning side of things was we generated a couple thousand different velocity models that represent these two-layer problems, and just found the lowest misfit between observed and calculated. And you can see from the image processing product here, the blue dots, and the hand-picked dispersion, the red dots, it's a pretty good fit. And the benefit was we didn't have to pick any dispersion. These are just some of the misfits or the RMS errors for VS1 and VS2 with our grid search approach. And once you generate these 2D models, or sorry, these two-layer models where you've got the Holocene deposits here over the top of these tertiary deposits, you can start looking at things like the impedance, which is this red line here, or the resonant frequency here, which is this black line. If we put all this together, there's a database of core holes that have found the base of the Holocene throughout the whole Charleston area. We gridded it. My student William did this. We measured shear wave velocities for a range of lithologies. We can use this relationship for this fundamental site response, which is this quarter wavelength relationship here, to generate a resonance frequency. And so we can apply this map with our velocity relationships to come up with a fundamental site response map for the whole Charleston area. So again, we did this, and we can do this without having to pick dispersion images. Moving on to this site in central Utah. This is what I call seismic characterization of a failed CO2 sequestration site. This is the product of my student John Yelton's thesis this past year, and we just submitted a paper on this this past month. These circles here represent the amount of their CO2 soil flux measurements. So the larger the circle, that means there's more CO2 that's naturally outgassing here. So this is not an artificial site. We're using this as an analog to a failed site. That's why I put the failed in quotes here. And we collected a series of seismic profiles across these here. You can see we also did some nodal work here, and that weight drop from the seismic source facility. We use that here, and I'll show you that in a slide. And this is the geyser that's located along the Green River here. It's a fun place to visit, but every few hours this thing erupts. Sometimes these geyser eruptions are not so energetic. Sometimes they only erupt by a meter or so, but there's CO2 infused in the water here, and every few hours we get cold water eruptions that occur. So some of the raw field data you can see just from a shock gather, you can see what I call a high velocity zone here, these elevated velocities here, or shorter, faster travel times. In the common offset gathers, you can kind of see slower zones here. Here is in the dispersion. You can see a nice low velocity zone here. You can see the dispersion, the changing velocities across this fault. It's called the Little Grand Wasp Fault. We collected some hammer seismic data here, and here's our reflection image. You can see this nice little fold, a little anticline here, and it's been faulted. We've got surface mapping to calibrate some of the surface expression of the faults. And the P-wave tomogram shows nice velocities that are consistent with the rock that we see exposed in the area. And you see this really nice 60-meter wide slow velocity zone. Through some rock physics relationships, you can convert the velocity into estimated porosity. We use this Castagnetol seismic velocity porosity relationship for saturated sandstones. We directly measured velocities for dry rocks and estimated their porosity. So we were able to get rock physics relationships for both wet and dry sandstones. We could pull out fracture density plots from this Clark and Burbank time averaged approach to estimating fracture density. And what we show is the reflection profile shows folded and faulted sandstones. And this is an inactive fault. It's delivering CO2 to the surface through the 60 meter wide high permeability damage zone, which is experiencing these elevated fluid pressures. So here's our elevated CO2. The larger the circle, the higher the CO2 that's outgassing. This is kind of background value here. And then this is blue line is another set of measurements from a different group. And you can see they nicely match this damage zone or low velocity zone. Why measure both VP and VS? Here's a profile that a sledgehammer profile that we collected where here's the VP tomogram, here's the VS tomogram, and then here's VPVS. And you can see that the velocities are going well above what I mentioned a couple slides ago, the kind of background measurements that we would expect for competent rock. And so I kind of pulled this plot together from some sources, including this USGS report by Lee 2003, where we can measure P-wave velocity for dry regolith, saturated regolith, semi-consolidated or fractured rock, semi-consolidated, saturated, so dry and saturated rock, and then unfractured rock. These are the P-wave velocities. And what I want you to make a note of is with P-waves alone, or with P-wave velocities alone, we can't really separate things like saturated regolith from semi-consolidated rock. There's too much overlap. But notice the shear wave velocities, which are relatively insensitive to fluid saturation. We see the same velocities for both dry and saturated regolith. They're off by maybe 5%. But when you look at the VPVS ratio, you can see that these values are significantly lower than the saturated counterparts. Same thing with semi-consolidated rock. And once you get into unfractured rock, it really doesn't matter because there's not that much pore space. But you can see, again, for semi-consolidated fractured dry rock, the VPVS ratio is typically below 2.5, and for the saturated counterpart, it's typically above that. And we see here that they are above 2.5 for the VPVS ratio. The P-wave velocities are upwards of 2,500 to 3,000 meters per second. So we conclude in this particular case that we have semi-consolidated or fractured saturated rock in this case. Without having VP and VS, we weren't really able to separate the lithology and the fluid components of this data set. And this is a kind of an ongoing project that my student Steve Slavicki is working on here, where we went and collected active source data with Galen here from using the active source from UTEP. And while we were doing that, collecting a couple kilometers with nodes, we also took our weight drop out there and planted 120 geophones up this gully here. And we just thumped the ground every 30 seconds for 30 hours. And we're looking at how the signals change as a function of time. So this is a 10-hour window here, and you can see some kind of funky arrivals here. So you would expect to see the travel times to be relatively constant through here. And we see some changes, and we're still exploring what those changes represent. And I'm kind of finishing up here. This is just a shot gather from downtown Seattle, comparing a cabled shot with our geodes with a nodal receiver. This is from Maureen Denal's nodal deployment that she collected a few years ago through the Harvard deployment. And you can see the reflections that we were able to pull out of the nodal receiver gathers. Or this is a receiver gather, I guess. And this is a shot gather here. So we are able to see reflectivity. This is, remember, the scales are slightly different here. So this reflector at 0.4 of a second, you can see is actually up here. So we were looking down over a second to see how much energy we could actually see out of that weight drop with the nodes. And then here's the question. I had to throw this image in. This is from some work up in Alaska on a boat. So this is marine data. Can we get high resolution images on land? You know, we can collect 100 kilometers a day on the ocean really easily. Can we do something similar on land? Here's an example from central Idaho. This is kind of one of these basins that parallel the passage of the Yellowstone hotspot. And we collected data with our land streamer here. You can see this image. We were able to collect 55 kilometers of reflection data in 11 days, so about 5 kilometers a day, using a 72 channel system. And we actually had a much longer streamer here, about 172 channels, but I think this is pretty good data quality. And being able to collect 55 kilometers with planted geophones would have taken us many, many weeks to do. And we were able to do this in 11 field days. So I'm not going to talk about the interpretation here, but you can see lots of faults. This is about finding blind geothermal resources. But we get really high quality data. So we're getting close to what we can do with a marine setup on land. So if you think of it, these land streamers are very similar to a marine seismic setup. And yes, seismology is scalable. We've built a small streamer here. This is William. Pulling our little tiny streamer here. And the cool thing about this is we can get near real-time mechanical properties of the soils. We can actually automatically pick the dispersion from these images, and we can generate in near real time soil stiffness profiles. This is across the Frenchman Fault. And here's the reflection image. This is a pretty low resolution image of it. It's just, I just did this in a very quick and dirty way the other day. And then you can see here on a dam, we're even higher resolution here with 100 hertz geophones. These are 40 hertz phones. These are 100 hertz geophones here, where we're trying to find voids beneath the dam. And then I'm going to end with what I said in my little abstract there is we're working our way towards autonomous acquisition. And so my question is the future of active source seismology with drones or with robots? And I showed this image here. Here's Andy Lamb. He's a professor at the University of Arkansas flying his drone magnetometer, where we collected this 4 by 8 kilometer drone data set in a single day. That's not something that we can do on land. And here we are, and I can play this little video here with one of our little robots here pulling our hammer and pulling our streamer. And if you hear that little noise, that's the active source. And then you can hear the computer recording of the signal. And that's that. So you can see our bigger robot here pulling our larger streamer, and then we've been doing some work in the snow. This particular drone is not really meant for concrete. It's actually designed with snow tracks in mind. So this is really the environment we want to work. We're not quite there yet, but we're getting really close. And so I'm going to end my presentation with that and take questions. So thank you for your time and your attention.
Wonderful. Thanks so much, Lee, for that fascinating talk. I would just remind folks tuning in that you're welcome to go ahead and send in questions via the Q&A box if you've got some questions. We did have one question come in via the chat about the availability of slides, and I would note that as this presentation is being recorded, you'll be able to access it on YouTube here within a day or two. We'll have that uploaded, so you're able to access that there. While we're waiting on some questions, Lee, it seems like this land streamer idea is really a powerful tool. And I like the comparison that you made with marine seismic data. I guess I'm a little curious if you could say a bit more about kind of some of the real world applications of these data sets. Particularly, I noticed that several of these were in cities, and you're looking at things like site amplification and things like that. Are these generally studies that are commissioned by local governments, and they're trying to work out hazard relationships or that sort of thing, or what are the typical use cases for this kind of
the example I show from Salt Lake was funded by the U.S. Geological Survey's Earthquake Hazards Program, and same with Charleston. And so we care about the slip history of faults in urban environments, because of course the closer you are to that hazard, the more vulnerable population centers are, and elevates the risk. And so I'm funded through the U.S. Geological Survey, or have been through those projects. That's been most of my urban work. I have done some work with municipalities, but for the most part in the urban environment, we're really focusing on urban hazards or urban resources. We've done some work with contaminant transport models, but where this won't work is, if you want to think of the critical zone community that goes out into the mountains and tries to understand water storage potential in the mountains, clearly the streamer is not the right solution for something like that. And you're just going to have to still plant geophones. I actually thought of showing a picture of the Boston Dynamics Big Dog robot here on this last slide, and I don't know if you all are familiar with that, but this thing can haul 800 pounds and crawl up the side of a volcano and do whatever. Maybe that's the future. Maybe we can crawl up, complex terrain with something like a robot. But I haven't done that, but it'd be kind of fun to imagine that.
Yeah, I appreciated this last slide here too, kind of thinking about the future of these kinds of active source surveys, and these robotics applications and kind of towing the complete package with the land streamer behind and the source right there. It seems like that's a really powerful combination. I would imagine that I know a lot of the drones use very sophisticated GPS on board to you can almost like draw a flight plan and have it follow a certain thing. is the land thing somewhat similar in that you can plot out a route and then it'll follow that predetermined plan where it's going to collect its data?
You can put the brains of a drone in any of these robots and essentially pre-program the waypoints, if you will. So yes, is the answer to that. I mean, so one thing you could envision is, I don't know how many of the audience is old enough to remember the CoCorp days of going across all of Nevada with Vibe and with a Vibe or a series of Vibes and geophones, but there's no reason why something like this couldn't crawl across the Nevada desert, mapping faults across all of Nevada or all of the Great Basin, so you set it on its way, and a couple of weeks later or whatever, you end up with a complete profile across the Great Basin. So that's what I've envisioned. Now, maybe someday we can make that a reality.
Yeah, it's a very exciting possibilities with that. It looks like we have a comment come in here from one of our hardware specialists at the PASSCAL Instrument Center. This is from Daniel Bustos. He says that drones would also be perfect for ground penetrating radar because the survey is already a set grid to begin with. So I don't know.
Yep.
I have seen a few other talks where they've flown aerial magnetic surveys before. I don't know that I've seen it with GPR, but it seems like this is certainly an area with a lot of potential for development as some of these new technologies take off.
Well, of course, radar is flown by shuttles, by in orbit. So yes, that works. We've flown helicopter-based radar, and yes, with the same little robot that you see here, we've pulled a sled with that houses our radar unit. So yes, you can absolutely do that. And especially, again, this is meant for snow, this particular, this is why we built this. And of course, going into dangerous areas like where there's avalanche potential or crevasses and the like, it's a lot better to take robots than humans in there. So this particular robot in the middle here was designed to traverse Greenland, and so, yes, it's absolutely possible for us to pull radar or even capacitively coupled resistivity sensors or whatever. So, yeah, I think the future is mobile. How's that for a?
I wonder, Lee, if you could say a little bit about, you said shallow active seismic work here. You mentioned that maybe this wouldn't be the kinds of tools you've talked about wouldn't be as appropriate for your surface geophysics application. But typically, what kind of depths are you looking at here in terms of the range of depths from which you're getting usable data back with some of these land streamer deployments?
For the tomograms, for the tomography, both VP and VS, we're seeing typically down tens of meters, and for the reflection images, we're seeing down hundreds of meters. So it's just So it depends, of course, on the data set and the area that you work, but those are typical scales. The problem with active source reflection work is oftentimes the depth of penetration is proportional to the offsets that you can image, because you've got to get outside of that surface wave window. And that means that you need really long streamers to image to greater depths. And so I showed that one slide from Seattle where we integrated the nodal data with the hammer data. In that case, we did not use the streamers, but there's no reason why you couldn't have one robot pulling a streamer and another robot pulling a source, or have a vibra-sized truck, a kilometer away from a series of these streamers that are occupying a city block, for example. So you could decouple the source and the receiver. So it just becomes more logistics to handle. Sure.
Okay. Well, it looks like we just got another question in here from Akram. This is wonderful talk. Thank you very much. How long does the snow robot last with batteries, and how do you track the locations of the streamer?
Well, the way we have this currently set up is I'm taking the video on the right here, and I also have, or one of the, I think Thomas was next to me operating the weight drop remotely with essentially a modified garage door opener. So you can completely automate these. Like this weight drop, we can set up to voltage modulate, so we can run it completely remotely, but we're standing right next to it in this particular case just because it's not ready for prime time. It's a good question about the batteries. You can see the 2 batteries that are mounted here. I don't have a good answer because I haven't run this thing long enough to know how many hours it works. You can see this robot in the middle here has solar panels on it. It was designed, actually inside the tracks, there are batteries on both sides. It's a huge battery bank in this. So the answer is it depends on what you want. I mean, you can obviously accessorize this with solar panels. You can add more battery power, or you can swap out batteries whenever you need to. So I don't know that I have a good handle on how many hours, like for example, a typical car battery would last, but hopefully I will know that answer soon. Yeah,
and as far as the position of the streamer, I'd imagine that that's kind of a function of where the robot itself is, because you can kind of work off from the distance of the line of geophones. Is that how you do it, or do you have a more precise way for precisely locating those geophones?
We run a GPS on our source typically, and so we can calculate the receiver positions. But you're right. I mean, if there's a gutter next to the road, the streamer wants to follow the gutter. It's kind of like with a marine streamer. If the winds are blowing one direction, your streamer tends to follow the which way the wind blows, and so it's not perfect. And sure, you could put more GPSs on the back like we do with marine operations to try to gain a better control of that. We just haven't done it. We typically operate these things with somebody at the back end, and there's a couple of reasons for that. One is just for safety. We don't want cars driving over it, and 2 is you can actually correct the position of the streamer just by pulling on the back end of it. These streamers are actually pretty light, so you can control them pretty easily.
Okay. Well, great. I think our hour is just about up, okay. So we'll leave it there. But just want to take an opportunity again to thank Dr. Lee Liberty for this wonderful and very fascinating talk today.